In this video, we're going to be subtracting radicals, and just to note, as always, that in order to subtract these radicals from each other, we have to have the same root. So the root has to be the same, the index must be the same, the radicand must be the same. So I'm just going to put on here, same roots required to subtract. Now we run into an issue right now, because notice that these are not the same, right? This is basically, we have a cube root of 2 and we have a cubed root of 54. So while the index is the same, we have this index of 3 and the index of 3, the radicand, the number on the inside, is not the same. So therefore these roots are not the same. So we need to go ahead and we need to simplify this first one to see if we can come up with something that we can combine with this cube root of 2. Now I'm going to go ahead and I'm going to use my favorite numbers, my prime numbers, because I like to prime factorization. So I'm going to go ahead and write 2, 3, 5, 7, 11, and 13, because these numbers will usually help you to factor these radicals. I would say 90% of the time or more. There's a few numbers that come up sometimes that are not in here, but most of the time this is going to take care of it. So I'm going to go ahead and create my number tree. I'm going to break this up, and I'm going to start with 2, because I always start with the lowest number unless I recognize a perfect square that exists in it. And right at the moment I don't see, I said a perfect square, a perfect cube, if that would be the case, because it has to be the power of 3, and I don't see one in there. But I'm going to divide it by 2 and see what happens. So I divided by 2 and I got 27. So 2 and 27. Now I am going to stop here because I recognize that 27 is what we call perfect cube root. In other words, there is a number that can multiply to itself 3 times to give me 27. So since I recognize that, I'm going to stop. I'm not going to go any further. And I'm going to rewrite this. So I'm going to rewrite this as a cube root of 2. And that's a surd. In other words, it can't be simplified any further. So there's nothing else we can do with that. But on the other hand, this one right here, 27, so cubed root of 27, I know that that can be broken down further. So right now what we have is I have these two roots being multiplied to each other, right? And I'm still subtracting this cubed root of 2. And we'll deal with the subtraction later, right? But we got to handle the multiplication first, and we got to convert anything that can be converted. Now I'm going to go ahead and just put an arrow, because I'm going to write this answer up here in the front. So I'm going to put this into my calculator. So if I hit math and go down to my cube roots right there that has an index of 3, I'm going to hit enter, and I'm going to put in 27, and it gives me 3. So really this one right here, right, we gotten rid of it, and it just turns into simply 3. And then what I'll do is I'll go ahead and bring what we couldn't change, right, the cube root of 2. So cube root of 2 minus the cube root of 2. Now we have the same root. So we can actually combine these, right? We can do some subtraction here. Now do keep in mind that although this one on the right didn't have a number in front, there is an invisible 1 in front of every root. So we do have a 1 there. So really this is like saying 3 minus 1. And 3 minus 1 simply gives me 2. So my final answer is this is 2 cube root of 2. Now I am going to check this answer right. As always, we can always check these answers if we're not sure that we did it right, because we can go back to our calculator. What I can do is put this into the calculator and then put this final answer into the calculator and see, do they both give me the same value. So let's try that. So I'm going to go ahead and I'm going to hit math, pull up my cube root, and I'm going to put 54 in there, and then I'm going to subtract and hit math, another cube root, and put 2. So when I subtract these, it gives me 2.519. So I'm looking for the same answer if I were to put 2 cube root of 2 in there. So I'm going to go and do that. 2 cube root of 2. Hit enter, and notice I get the exact same answer. So that verifies that I did it right. This is correct. It is written as an exact answer because it has a radical in it. And I'm done. So let's go ahead and go on to example 2 now. Once again, when we're doing the subtraction, I noticed that the roots are not the same. Again, we have the same index, right? We have an index of 4. and an index of 4 over here. So this is what we call a fourth root. However, we have 48 for the radicand here, and we have 3 for the radicand on this one. So let's go ahead and let's see if we can break this one on the left down so that we end up having a fourth root of 3 so that we can subtract them. So let's go ahead and do that real quick. Now I'm going to start with my favorite number. Again, I had already written the numbers earlier, and so I'm going to start with 2. So I'm going to see, can 48 be divided by 2? And it can. It gives me 24. So I'm going to go ahead and start writing these down. So I have 2 and 24. Alright, and then I'm going to go ahead and divide 24 by 2, because 24, at least I can't think of a number that would be cubed and go into there an even amount of times. So we'll just continue the process. And I get 2 and 12. And I'm going to do that one more time. So I'm going to divide 12 by 2, and it gives me 2 and 6. And I'm just going to keep going until we hit a prime number. So let's say that you're looking at this, you didn't recognize any cube roots, or what we call perfect cube root, and so you just keep going until you hit a prime number. Now we have hit a prime number, right? Our prime number is 3. So I know that this is everything. So I can go ahead now and I'm going to rewrite this. And when I rewrite it, I'm going to start, notice we're going to use all the numbers on the left of the number tree and the one on the bottom right. So in other words, I have a fourth root of 2. I have a second one of 2 again, and another one, and another one. And then last of all, we have 3. So fourth root of 3. Now that we've gotten this far, remember that the index indicates how many of these radicals we have to have multiplied to themselves to become the radicand, the number that's on the inside. And since our index is 4, I'm going to circle it up here. We have an index of 4. For every 4 roots of 2, it's just going to turn into 2. If our index was 3, well then it'd be for every 3 it would turn into 2. If we didn't have an index, it would mean it's 2, and for every 2 it turns into 2, and so on. So now that I see 4 2's, 1, 2, 3, 4, that's simply going to turn into a 2. And what's left over is this fourth root of 3. Okay, at this point, that's actually the same, notice that we had over here on the right side. So I'm going to bring this one down, because now, since the roots are the same, we can actually subtract it. So this is minus 4 root of 3. Now do keep in mind that again, in front of every one of these radicals there is an invisible 1 if you don't see a number in front of it. And so we actually have 2 minus 1. And 2 minus 1 just leaves me with 1. So my final answer is a fourth root of 3. Again, we could check this with the calculator to make sure that we're correct by simply taking this initial expression, putting it in the calculator, seeing what its value is, and then checking our final answer. Now, the other thing I want to tell you is I know now, seeing 4 2's here, that if I would have broken this up as 3 and 16, in other words, if I would have used my prime number of 3, so let me show you. I'm going to do 48 divided by 3. I would have got 3 and 16. And 16 is a perfect fourth root. In other words, if I were to take 16, I'm going to hit math. Notice on this root it just has an X because I can put any index I want. I'm going to put a 4. And I were to put 16, it's going to simply tell me 2. And that's because 2 multiplied to itself 4 times gives me 16. Now some of you may have realized that as you were taking this apart, but I didn't until I broke it apart. And then once I seen I had 4 2's, I said, well, what's 2 times 2 times 2 times 2? And I thought, well, that'd be 16. So that's just something else, right? If you recognize a perfect fourth root, a perfect cube root, a perfect square root, you can always pull those out instead of continuing to break this down until you get to a prime number. But like me, if you looked at it initially and you didn't see that in there, you weren't able to recognize it, well, just keep breaking it down with your prime numbers until you get to a prime number. And that'll work as well. Either way, you're going to get the same answer. I will go ahead and validate in this video just to show you how we could check it, just to refresh your memory. I am going to hit math. I'm going to go down to this fifth option where it says X for my index, hit enter, put my 4 in there, and then I'm going to go to the right and put in 48, right? Because that was that initial value. Then I'm going to click to the right, hit minus, hit math again, go down, change that and put a 4 in my index, and then put the 3. And when I hit enter, it gives me 1.316. Now I'm going to take my final answer that I did just to compare it, to confirm that it was done correctly. So I'm going to hit math, go down, put a 4 in there, and then I'm going to put 3. Notice that the answers are exactly the same. So I did the work right, and this exact answer is correct.